welcome back to this channel. In this video, we are going to focus on the Dalton's law and discuss the tutorial question number 6 up to question number 9. Okay, let's continue with question number 6a. State the Dalton's law of partial pressure. The total pressure of of a mixture of non-reacting gas. Okay, so keyword over here is non-reacting gas. So you have to make sure the gases in the similar container or in the same container, they are not reacting with each other. Is the sum of the partial pressure of the all components. For example, if the container consists of gas A, B, and C, so the total pressure will be total up the partial pressure of A, partial pressure of gas B, and also partial pressure of gas C. Look at one diagram here. All these three containers have similar volume, which is 5 liters, and then the temperature also at 20 degrees Celsius. So let's say if individually the hydrogen gas are inside in this container, the pressure that asserted is 2.9 atm. If individual helium are placed in this container, the pressure asserted is 7.2. However, if I mix these two gases together at same container, their total pressure will be equal to 2.9 plus 7.2. And where we notice here is 10.1 atm. And where the amount of the gas are not changing, even though after they mix together, and the volume of the the volume of the container is still the same. Okay, then maybe you will ask, then how I'm going to find the partial pressure of the gas A? Yes, basically we are applying the ideal gas equation, PV equal to nRT. If you want to refer to the partial pressure for gas A, so the number of mole that you refer to must be number of mole of gas A. While if you want to look for the partial pressure for gas B, then here will be number of mole of gas B. While the volume and also the temperature, because they are in the same container, so their volume and their temperature supposedly are the same. By adding the partial pressure of gas A and gas B, then you will get the total pressure of the system. So sometimes you maybe will be given the number of mole of gas A and number of mole of gas B and also the total pressure. So if you are given this information, then you're also able to determine the partial pressure of gas A by using the mole fraction of gas A multiplied with the total pressure. So basically, these are the few formula that will be used when you are answering the question related with the Dalton's gas law. Okay, the first one is derived from the ideal gas equation. The second one is based on the definition of the Dalton's gas law. And then the last one, we relate the partial pressure with the mole fraction and also the total pressure. Now let's proceed to tutorial question 6b. A 3 liter of closed cylinder, so we have the volume, contain a mixture of 1.25 gram of nitrogen oxide and also 33.95 gram of nitrogen dioxide at 27 degrees Celsius. So this is the temperature. Assume that the gas are not reacted with each other. So basically we can see that it say that not reacted with each other. Before we continue with the question, basically we can think about this question is related with the Dalton's law. Okay, next part of the question, we are going to calculate the total pressure of the gas. Means that we are going to get the P total. So as just now we mentioned that if we want to calculate the P total, actually is the partial pressure of gas A. In this case, maybe it's the nitrogen oxide, and then plus with the partial pressure of NO2. Okay, however, if I want to find out the partial pressure for the nitrogen oxide, I may use the equation PV equal to nRT. So in this case, I can use PV equal to nRT. So volume is given, temperature is given, gas constant also considered given. So we need to find out the total pressure. So means that we need to determine the number of mole of total number of mole of the gas before we can calculating the total pressure. So because this is the total pressure, so over here we will need to find the total number of mole. So total number of mole in this case is number of mole of nitrogen oxide plus with number of mole of nitrogen dioxide. With the mass given, we divide by the molar mass, we will able to get number of mole. So 11.25 gram divided by the molar mass of the nitrogen oxide 30 plus with 33.95 gram of nitrogen dioxide divided by 46 the molar mass. So the total number of mole will be 1.113 mole. Then I am going to substitute the value into the total number over here. So, and then we will convert the degree Celsius to Kelvin. So when we press the calculator based on the PV equal to nRT, and where we know the volume, number of mole, total number of mole, gas constant, temperature, then the total pressure for this container is 9.14 atm. Question 6b2, calculate the partial pressure exerted by each gas. So in this condition, again, we have nitrogen oxide and also nitrogen dioxide. So basically, we have two methods to calculate this answer. Either you can use the ideal gas equation, PV equal to nRT, but this time when you want to look for the partial pressure for NO, so you have to make sure the number of mole that you substitute here is referred to number of mole of NO. While you're looking for the partial pressure of NO2, then you are going to substitute the value of number of mole of nitrogen dioxide gas. This is the first method that we can use. Or since you are given the, since you are calculated the total pressure, then let's say if you want to find the partial pressure of nitrogen oxide, you are able to calculate based on the total pressure with the mole fraction of NO multiplied with the total pressure. Okay, so just now we already calculate the number of mole of the nitrogen oxide will be 0.375, and then over the total number of mole, which is 1.113, and then multiply with the total pressure 9.14. So the partial pressure for nitrogen oxide will be 3.08 atm. So you can use the similar formula to calculate the total pressure, the partial pressure for the nitrogen dioxide gas, or you can basically use the formula total pressure equal to a partial pressure of NO plus partial pressure of NO2. So in 6b1, we already calculate the total pressure, and then we just calculate the partial pressure for the nitrogen oxide. Then the partial pressure of the nitrogen dioxide, we're going to use 9.14 total pressure minus with the partial pressure of the NO, which is equal to 6.06 atm. Question 7. Tank A and B are connected by a closed valve. So means that at this moment now here, tank A only consists of CH4, while tank B consists of nitrogen gas. Both tanks are at the same temperature. The valve is then turned on to allow both of the gases to mix together. So means that some of the methane gas will go to the tank B, while some of the nitrogen gas also will go to the tank A. So at this moment, the temperature and also amount of the gas are fixed. But what will change? The volume of the gas changing, and also the pressure of the gas is going to change. So when this case happens, we are going to use Boyle's law P1V1 equal to P2V2 to calculate the new pressure for the CH4. So before the valve is open, the pressure for the methane is 3.5 atm, while the volume is 7.5 liter. Now, the new pressure for methane after the valve is open, we have no idea, but the volume is the total volume for 7.5 and 5.75, which is equal to 13.25. So when we press the calculator, the pressure of the methane after the valve is turned on will be equal to 1.98 atm. So repeat the similar state for the nitrogen gas. We're also going to use P1V1 equal to P2V2. So when the valve is closed, the pressure for nitrogen gas is 6.2 atm, while the volume is 5.75 liter. After the valve is turned on, the new pressure we have no idea, but the volume of the container is become to 13.25, which is similar with tank volume of methane. So the new pressure for nitrogen gas is 2.69 atm. Continue with question 7. So after we determine the new pressure for the CH4 and also new pressure for the nitrogen gas, which is 2.69 atm and 1.98 atm for methane. So next part of the question let us to determine the ratio for the number of mole of methane to the number of mole of nitrogen. Okay, so with this case, because now we have the partial pressure for CH4 and partial pressure for nitrogen gas, and we also know the total pressure. So with this information that we have, we are able to determine the mole fraction of CH4. So we are going to use the formula partial pressure of CH4 equal to mole fraction of CH4 multiplied with the P total. So you are given the P total and the partial pressure of CH4, then we are able to determine the partial pressure, the mole fraction of CH4, at where we are going to use 1.98 over 1.98 plus 2.69, which is the total pressure. And then when we press the calculator, the mole fraction for CH4 is 0.42. Okay, then we assume that total mole fraction is equal to 1. So in this case means number of mole of CH4 will equal to 0.42, while number of mole for nitrogen will be 0.58 mole. Here we want the ratio methane towards nitrogen. So we are going to use mole of CH4 ratio to the mole of nitrogen, which is 0.42 over 0.58, and then we can simplify become 1 to 1.38. So this is the final answer. There is another application of Dalton's law. Based on this diagram setup, we can know that this is the water displacement method, or when sometimes in the question they will mention that the gas was collected over water. So at here, you will know that this is the pressure that we measure, and then the total pressure, which is the gas and also the water vapor, will equal to P total. Now let's look at how the Dalton's law can be applied into the water displacement method. So this is the diagram for the water displacement method. So the atmosphere pressure can be equal to total pressure. Okay, as this inverted gas jar, it still can maintain like this, means that inside this gas jar consists of the pressure exerted by gas and also the pressure exerted by the water pressure, because in here we have the water, so some of the water may escape as the vapor. So here we have pressure exerted by the gas produced from the reaction and also the water pressure. So to find the pressure of the dry gas alone or the gas produced, so we are going to use the concept of Dalton's law, at where pressure of gas produced will equal to total pressure minus with the pressure exerted by water vapor. So all this one will be given in the questions. By applying what we learned in previous slide, so let's look at tutorial question number 9. A sample of oxygen gas is collected over water. So this one is water displacement method, means that we are going to apply the Dalton's law, at where the P total will equal to P pressure of the gas plus partial pressure of the water vapor at 20 degrees Celsius, and then the pressure is 738 torr. So to keep in mind that if the question given like this pressure is not referred to the pressure of the gas, but it is referred to the total pressure or partial pressure of atmosphere. And its volume is 310 ml. Given that the vapor pressure of water is 17.5 torr, so what is the partial pressure for the oxygen gas? So from here, the question give us the P total and also the water pressure. So by rearrange this formula, we will able to calculate the partial pressure of the oxygen gas is 720.5 torr. So in this question, if you didn't convert to the unit of ATM is okay, because the question didn't emphasize what is the unit of pressure that required. They just asked us to determine the partial pressure for the oxygen gas. Okay, question B, what would be the volume of the oxygen gas when the oxygen gas is dry at STP? So as we know, STP means that standard temperature, the temperature is 0 degrees Celsius, and then the standard pressure is 1 atm. At where if we try to relate with the unit of torr, 1 atm is equal to 760 torr. Okay, so what is the volume? We have no idea. But before the gas is dry at the STP, the temperature is 20 degrees Celsius, and then the pressure of the gas is 720.5 torr, which we calculate over here, and then the volume given here is 310 ml. So from here we notice that temperature is changing, Pressure also changing. Volume might be changing as well. So when we have two values like this, we can either use Avogadro's law, Boyle's law, Charles' law, or combined gas law. But if we use the formula of ABC, then there are supposedly another two parameter must be kept constant. But here only have one parameter keep constant, which is the amount of the gas is keep constant. So we are going to apply the combined gas law. So when we do this again and again, the temperature must be converted to the unit of Kelvin. So after that, we substitute the value into the formula. We will notice at STP, the volume of the gas that is able to collect is 269.2 ml. Question number 8. A 500 ml vessel, so we have the volume containing 1.35 gram of chlorine gas, which have the pressure of 760 millimeter mercury. When a certain amount of the gas is added, the pressure will rise to the 865 millimeter mercury. So means that this is the P total for the partial pressure of chlorine gas and also partial pressure of oxygen gas. While this 760 is the partial pressure of the chlorine gas. Assume that the gases do not react with each other. So actually this question already gives us the hints that we are going to apply the Dalton's law of partial pressure in this question. And the temperature remain constant. Then we need to calculate the mass of oxygen gas. So maybe some of us will think that, okay, we have pressure, we have volume, and then we also have need to find out the mass. Some of us may think of we can use the formula PV equal to nRT. So let's check, is it we can use the PV equal to nRT ideal gas equation to solve, or we have to use the Dalton's law to solve this question. Okay, so when we look at here, we need to find the mass of oxygen gas. Number of mole of oxygen gas we can expand to mass of oxygen over the molar mass of oxygen gas, and then multiply with the R, temperature, pressure of the oxygen gas, and volume of the oxygen gas. So based on the question here, basically I think you will get the idea that the partial pressure of oxygen will be 865 minus with the 760 millimeter mercury. So means that we have the partial pressure for the oxygen. Volume 500 ml. Yes, we have. Even though in the container consists of chlorine gas and also the oxygen gas, but the volume of the oxygen gas will still same as the volume of container, which is 500 ml. Okay, mass of oxygen gas, let's say, is the one that we are going to looking at. Molar mass, as we know, atomic mass for oxygen is 16, so we also can determine the molar mass. R, gas constant, is fixed, so we can substitute in 0.08206 liter atm per mole per Kelvin. And then the last one is the temperature. When we look at the question here, the question only mentioned that the temperature is remain constant, but they didn't let us know what is the value of the temperature. So means that we are not able to use the ideal gas equation to solve this question, because in one formula there are two unknowns. So again, that's why we are going to use Dalton's law to solve this question. Okay, as we discussed just now, we already know that we are going to use the Dalton's law. So for the Dalton's law, we have two parts. Either we use the formula P total equal to partial pressure of oxygen and total up with the partial pressure of chlorine gas, but we are not using this formula to solve the problem, and in the formula here we are not able to determine the mass of oxygen gas. So we have to apply another formula, partial pressure of oxygen gas equal to mole fraction of oxygen multiply with the total pressure. Okay, so from here we are going to know that Mole fraction of oxygen gas will be equal to number of mole of oxygen over number of mole of oxygen plus with number of mole of chlorine gas multiplied by the P total, and then this is the partial pressure of the oxygen gas. So from the question, we roughly already know this is the P total, and then this is the partial pressure of chlorine gas. So when the P total minus the partial pressure of the chlorine gas, which equal to 105 millimeter mercury, will be the partial pressure of oxygen. Number of mole of oxygen, we have no idea yet, so we remain it as unknown. But the number of mole of chlorine will be 1.35 gram over 2 times 75.5, and then multiply with the total pressure, which is 865 millimeter mercury. So one formula only have one unknown. So based on this calculation, after you calculate, you will get the number of mole of oxygen gas is 2.62 exponent negative 3 mole. Okay, but the question is not ask us to look for the number of mole, they ask us to look for the mass of the oxygen gas. So we are going to use the number of mole, 2.62 exponent negative 2 mole, multiply with the molar mass, 32 gram per mole. End up, we will get the mass of the oxygen gas is 8.38 exponent negative 2 gram. Okay, this is the final answer for tutorial question number 6 up to question number 9. Thank you for watching this video. We will see you again in next video. Thank you.